Hi, I'm Adam Costi,
And I'm Evan Knapp.
and today we're going to be talking about doubly fed induction generators, also known as DFIGs. To give you an overview of what we will be talking about today, we are going to be going into the structure, operation, control, and application of a DFIG.
As you can see on the image to the left here, that is an image of a commercially available DFIG generator. First thing that we're going to talk about or break down is the structure of a DFIG. So what makes these unique compared to other induction generators is the fact that it has two three-phase windings on both the rotor side and stator side, where in most applications, only the rotor side has three phases. What this allows for is a variation in synchronous speed, which isn't available on other types of generators. What this allows is a plus or minus 30% operation of synchronous speed, which is a very unique feature to the DFIGs. But some of the limitations of the synchronous speed, the reason why it only goes between plus or minus 30% is because with a varying magnetic field, we have, as you can see on the image up in the upper left there, we have a field limit and an armature limit. Both of those are heat related. So as you change the field in the generator, you actually generate more heat. As you can see, there is a line showing the real power and a line showing the reactive power. As you can see, as you raise the reactive power, you get closer to the field limit. As you raise the real power, you get closer to the armature limit. And based off of that, the controller will try and mediate that to keep it in those ranges so you don't overheat the generator.
DFIGs are used in windmills. As you can see off to the side, there's a nice row of windmills there, and they are typically have a higher starting cost to install them because they cost more in general than other types of induction generators. But in the long run, you will save money when you use them.
Now we're going to take a look at the control aspect of a DFIG generator. As you can see in the upper left of the image here, we have a squirrel cage induction machine as well as the doubly fed induction machine. This is obviously a smaller scale used for laboratory experiments. The squirrel cage induction machine is used to simulate a turbine rotating in order to generate the electricity that the induction machine would normally generate. As you can see, looking at the transient responses down in the bottom left, the third line down on the leftmost set of transient responses is the voltage output. And as you can see, the second line or the second graph on that same set of graphs shows the changing in rotor speed. So as you can see, as the rotor speed changes, so does the voltage, but only for a slight second is it out of the operating voltage that we want it to be. That's what's so unique about these. The synchronous speed of the rotor can change. As looking at the bottommost image, the actual rotor speed changes, but you still get the same voltage at the output. And as you look at the other set of images right to the right of that, that shows a fault in a system, and as you can see, it can control that fault really quickly and get you back to the voltage and the operating voltage that you want. So what's nice is the controllers for this allow for a quick response time to wind changes as well as fast control of any kind of fault that you might have in the system.
I'm going to talk about operation. First thing I'm going to talk about is how the whole windmill works in conjunction with the DFIG. First, you're going to have your wind turbine, which has angled blades to catch the wind, and those blades are going to spin around and generate rotational energy, which will be converted into a type of mechanical energy within the gearbox. And then that mechanical energy within the gearbox is going to be converted into a various AC current inside the DFIG. And that DFIG is going to be connected to the power grid, and it is also going to be connected to the rotor side converter, and that rotor side converter is also going to be connected to a grid side converter, which will be connected to another transformer going back to the grid as well. And how the synchronous speed changes is depicted in this image on the left here. When the rotor and the stator have different magnetic fields going, they're varying, but they're going in opposite directions. They're varying in opposite directions at the same time. That's going to actually induce a faster speed on the rotor within the defig. This is useful because when the synchronous speed of the defig increases due to, say, a stronger wind speeds than you expected and the turbine increases, the synchronous speed of the generator is going to go up. And with a defig, you're not going to have pushback from the power grid like you would in another induction generator. This is good because that pushback from the power grid will cause a lot of strain on the gearbox. And when that gearbox is broken, it will need to be repaired, or your windmill is essentially broken. Defigs come in two models, the brushed model and the brushless model. The brushed model is very large because it's used in big electrical power generating systems such as windmills, which can generate up to 1 or more megawatts of power. But it also has a lower initial installation cost than its brushless counterpart. But that does come with the caveat of it requires a slip ring maintenance, because that slip ring and the brushes will wear out over the years.
Next, we're going to take a look at the brushless model. So as you can see in the bottom left there, we have the progression in brushless defigs in size. As you can see, originally it was used as a smaller, more laboratory style experiment design in 2002, 2003. As you can see, it shows the progression of them over time from that smaller induction machine into a much larger one that actually could be used inside of a wind turbine. If you look in the top left corner here, you can see an actual induction motor and how much smaller it is in comparison to the one that we were just looking at. Yes, this is a unit meant to generate less power than the one that we previously showed you, but they are more compact because they don't have to have the extra size for the brushes and everything of the such like that. They use more microcontroller designs, which allow for to cut down on overall size. They are definitely more expensive initially with the complex controllers that they use, but they are much more efficient, as all brushless machines are. The nice thing is also they'll have less maintenance over time, so repairs in general are really a non-issue unless you were to have something catastrophic happen.
Some final thoughts on defigs is that they're mainly used in windmill applications, and if you're starting up a wind farm, it would be a better idea in general to use defig generators, because over time you're going to have less repair costs, even though they may be a bit more expensive initially.
And as we kind of showed before, what's unique about them is their controllers. So since it has three-phase power in both the stator and the rotor, that allows for the varying synchronous speed. That's really what's so unique about the defigs and makes them such a desirable new use case that's come around more recently in the past couple years.
If you have any more questions about defigs, just leave a comment on the video and we will respond to you when we can. Thank you.